Now, what we also learned about the Fourier transform is it's a great way to take derivatives. If you remember, to take a derivative, I can say the Fourier transform. So if I want to calculate the nth derivative of something, here's how I could do it. Fourier transform, the function. So we have this relationship here. And what does this relationship say? If I want to calculate the nth derivative of something, what I could do is take the function, Fourier transform it, multiply by ik to the nth power, inverse Fourier transform. By the way, this is going to be about the most accurate way to compute a derivative for you possible, if you can get away with periodic boundary conditions. It's beyond algebraic accuracy. So if you use finite difference, you get delta x squared accurate, or delta x fourth. This is exponentially accurate, provided you can live with the boundary conditions. So let's go ahead and take a function and calculate its derivative. So the function I'm going to work with is my favorite. I don't know if you have a favorite. Sech, hyperbolic secant. It's a little bump as well. Very simple function. By the way, its derivative is minus sech times tanh. Okay? Now what we're going to do is we're going to have a plot here of the function itself, xu, versus, and we'll make that in black, which is k. B is for blue. X, ud, and we'll make that in magenta. I like magenta. That's nice. Okay. I have a lot of pink crayons at home because my daughters love pink crayons. They've switched to blue recently. The older one. The younger one's still kind of into pink and purples, but we're moving up on the color charts slowly. There is the function. There is its derivative. Okay? And I want to calculate those things. These are exact. I want to see how well can I do by approximating this magenta curve with the FFT transform. So here's what we're going to do. We're just going to say, okay, I want the derivative. First, I need the k values. Let me write them here. And this here little line of code, I could even like say this sweet little line of code is something you want to keep in your head. 2 pi over L times 0 to n over 2 minus 1. And I'll tell you what this is in a moment. Minus n over 2 to minus 1. These are your wave numbers. So a couple things we've got to do. First, we have to understand that the FFT is in this shifted frame. So we take our wave numbers and we shift them. The wave numbers should go from negative k values to positive k values. Second thing, the FFT thinks you're working on a 2 pi periodic domain. I'm not. I'm working on 0 to L. So I have to rescale from 2 pi to L. So the factor of 2 pi over L is all about the rescaling. These integers are the wave numbers. So this is like your cosine 0x, cosine 1x, cosine 2x. Okay? But I have to shift them. So when I shifted, so normally this would be over here, that would be over there, but since I shifted, I've accounted for the shift. By building it this way, I've set up everything already to be in the shifted frame.
Sorry, you're labeling the x-axis here?
The x gets shifted in k. So you take your x locations in the k. It's the x-axis of the frequencies. Yep. It is k. It is k. You're now in frequency space. Yeah.
And so if you did FFT shift, I mean,
if you do FFT shift, and then this is just frequency components that go from negative,
so whatever you would reverse these, right? I mean, then you would go from minus to plus.
That's right.
Okay.
Mm-hmm. Now, once you have this, you can say, okay, I want to find a derivative. No problem. So first of all, you take the Fourier transform of the function. Second of all, you'd say, okay, if I want the first derivative, call it u1 dt. So first derivative transform is equal to I times k dot times ut. Okay? It's a vector multiplication, so put the dot in there. It's not an inner product. Okay? And if you want the first derivative, then you just have to say IFFT. Done. Okay, so let's plot it on here. Plot x versus u1d in green dots. Okay? 1, 2, 3, go. Now, I'm going to zoom. All right, ready? Ready? There's the zoom. Boom. And let's go see how I did. Oh, my. Do you guys see that there's green dots on there? Okay, not very well, probably. Okay, so let me make, I'll tell you what. Let me make green circles. You'll be able to see that better. How's that for rocking it with MATLAB, huh? Check it out. I said that the magenta is the exact solution. The green is, in fact, your approximation to that solution numerically using FFT. And I can zoom in. And look at that. Oh, man, that dot doesn't want to fall off of there. Doesn't want to fall off. Oh, I got it to fall off finally. But by the way, look on the left here. You see the axis values? Those are like 10 to the minus 6 accurate. It's pretty amazing, right? So if you do something like second order, find a difference, you'll fall off a lot earlier, like at 10 to the minus 2, 10 to the minus 4, something like that for this number of points. Okay? So this thing will stick on there for a lot longer. And that's exactly what you want. But you can see that it's an approximation. All right. A couple things. Let's violate some conditions. This is a nice function that goes to 0 at the boundary, so the periodic boundaries don't really play a role. So let's just do this. Let's take L to be 4. So now I'm not really decaying at the edges very well. See this here? Let's zoom in on part of this thing. See that this thing isn't really periodic anymore? So now what's happening at the boundary? Problems. Okay? See over here? It's trying to be periodic. Whenever you have discontinuity in periodic functions, you get this thing called Gibbs phenomena. Gibbs phenomena are strong oscillations near discontinuities. And that's what you see here. So you'd say, oh, that's really bad. But look, I mean, amazing. It does great in here. It just gets out here, and you kind of go, whoa, bad news. That's just because you've violated periodic boundaries. So that's kind of it for the Fourier transform business, taking derivatives and all that stuff. I mean, if I wanted to take even a higher derivative, it's easy. You just take bigger k's, right? So here we just multiply this. Suppose I wanted to calculate, I don't know, fifth derivative. Let me just do that. It's going to give me the fifth derivative. So now let's plot the fifth derivative here. And so now I have the fifth derivative, and let's take this back out to be 20, and was that oh, did I not? I got something wrong here. I view D here. I don't have that still, right?
Next you have a line 14.
Line 14. I'm missing a parentheses. All right, thanks. What is it? No. Here. Oh, yeah, I got an extra one. There we go. All right. Okay. Boom! All right. There's the fifth derivative. See how much trouble it's having at the boundaries out there? So you need to get something going to 0 more. Anyway. Well, in the middle, it's going to oscillate a lot because when you start taking higher derivatives, right, the fifth derivatives, I haven't plotted the exact solution. So actually, it's probably okay. In fact, let's do the following now. Let's plot this and just let's take a few more 512 points, and we will now plot it with a green line like that, and boom. If you do that, this is what the fifth derivative looks like. You can see you're having problems with boundaries, but just let's look in here and pretend there's nothing happening out there. So these are what the fifth derivative looks like. Okay? All right. By the way, check this out. Warning. I'm sure you've gotten some warnings. Imaginary parts. What? What? Yes, they're imaginary parts because you got this round off going on, 10 to the minus 16th, and you're ignoring it. Awesome. All right. There you go. So let's kill that.